Motors, fans, and pumps have another management opportunity, energy management opportunity to consider. And that's the fact that the amount of the amount of energy that they consume are directly proportional to some interesting things that we pay them to do. So when we look at motors, when we look at fans, and when we look at pumps, we are talking about devices that rotate, right? Motors rotate to spin a shaft. Fans rotate to move flow. So this is, if you're spinning a shaft, that's sort of like RPM, okay? Revolutions per minute, right? So this is like shaft rotation. And you're going to put energy and you're going to pay for the shaft rotation to come out. Fans, what are you paying fans for? Fans, you're moving things, right? This is flow. And that flow is going to be, can be measured in, meters cube per second, or liters per second, right? And same with pumps. Pumps, you are putting in rotation in order to make something flow. So let's say this could be like flow in meters cube per second, or in liters per second, if you want to put it like that. And let's say we're paying for some rotational input here, and we're getting some flow out. And again, flow is liters per second, or meters cube per second. But these are what these devices do. They are things that rotate to do other things, to either move some flow. We can be moving it linearly in a pump. We are moving it axially to our rotation in a fan, and we are we're moving rotationally in a motor. Yes, we're paying for electricity. We're getting rotation out. So if we can change the speed, if we can vary the speed of these devices, and we can vary how much money we're putting in, how much power we're putting in, then we can vary, then we can vary the amount of pumping or blowing, or rotation coming out. So another energy management opportunity is variable speed drive. So I just want to kind of put some math around this fantastic opportunity of variable speed drives, because nowadays we have automation systems which can very easily, very readily put in a signal that is not just off or on. It varies the voltage level in order to make these motors, fans, and pumps work. Variable speed drives are a reality. So let's look at what they actually get for us. So if we look at flow, we can see what is flow proportional to. So let's see, flow is sometimes liters per second, okay, or meters cubed per second. But let's say we want to vary the amount of flow, and this is our new flow versus our liters per second old. That's going to be directly related to, or we could put it in meters cubed per second of flow new over meters cubed per second of flow old, is directly related to the RPM that we're paying for, right? To the revolutions of, say, a fan. Okay, say a fan or a pump, the RPM of the fan or pump. New versus old, right? Now, but if we look at pressure, let's say we want to vary the speed on a pressure related device, then the pressure new over pressure old has the following relationship. If we were to derive this from first principles and we look at the difference at the effect of pressure on the change in rotation of one of these devices, such as a pump, then the speeds, oops, then the speeds RPM new versus old is actually a square relation to the amount of pressure that you're going to get out. So the square of the speed change, of the rotational speed change, is proportional to pressure itself. And the flow relationship, liters per second new and old, is also a square relation. All right. But if we look at power and speed, and again, we could derive all of these from first principles, and these are called the affinity laws. Affinity laws of pumps, fans, and motors. And we can use our basic physics to prove these. If we looked at those, how they relate to RPM, then the relationship is actually cubic. If we were to take out all of the other variables and look at our power and our flow or our rotational speed, it's actually a cubic relationship. And same with that of flow. Same with that of flow. We can do our flow in meters cubed per second, or if we want to stay in the imperial units, we can do that in liters per second. And these are the affinity laws for pumps and fans. So what do they say? What is my point here? My point is that the affinity laws are pretty special. We can say that a flow rate, if we vary the speed, and remember the speed is what we are paying for here. If we vary the speed, we can directly vary the flow. If we vary the speed or flow, it has a squared relationship to pressure. If we vary the speed or flow, it has a cubed relationship to power. So, in conclusion, why is this good for us? This is good news because to save a significant amount of power, we want to look at this cubed relationship. To save a significant amount of power, we can lower the flow rate of pumps or lower the RPM of motors. So the overall conclusion here from an energy management perspective is to save a significant amount of power, lower flow rate. Lower the flow rate of pumps. or decrease RPM of motors? If you can. Of course, you can't go through every plant and decrease the RPM of motors. Can you live with an industrial process that has slightly lower flow rate? And that's that it depends on the process, and you need experience as an energy manager to know what can you do. But are there some flow rates that are set higher than they need to be? Are you filling a basin at the beginning of shift where nobody is waiting for it to be filled, and it could have taken all shift at a lower flow rate, and we pay a significant amount less for the kilowatts that are required to fill that basin? Can we decrease the RPM of some motors? Will it, if the process is not a bottleneck, can we run some motors slowly because it's not a bottleneck and it's waiting for some other processes that are the bottlenecks? Can we decrease that RPM and get that significant change in the power required? So that's why motors, fans, and pumps become a very big opportunity to change or to reduce the power consumed if you can drive them at a variable speed. Now, most motor speeds and motors, fans, and pumps are variable speed now, but are they being operated at the lowest rates possible? It's a low-hanging fruit of energy management to be able to figure out if you can lower any of these.